In this chapter, we will see what is matrix transpose. The process is called transposition, and the result is transpose. We will see what it is, how to compute a transpose matrix, and what is it good for. Consider a square matrix with the elements, say, 2, 3, 5, 4. Then the transpose of this matrix, denoted by A sub t, will be, we rotate the matrix about the principal diagonal. So 2, 5, 3, 4. In this case, the entries 5 and 3 swap the position. In general, if we denote the transpose matrix B, then the element on the row I and column J of the result is equal to A sub J I. You see these two indices change a row. What was the number of the column is now the number of the row is now the number of the column, and vice versa. So this is for a square matrix. It works even for non-square, for rectangular matrices. If we have the matrix, say 1, 2, 3, 4, 5, 6, then the transpose of this 2 by 3 matrix will be a 3 by 2 matrix. And you can imagine we read a row and we write a column. 1, 2, 3, 4, 5, 6. And as we can consider a vector a special case of a matrix with just one single row or one single column, transposition converts a row vector into a column vector and vice versa. So if we have a vector x arrow, say with coordinates 1, 0, 5, then the vector x arrow transposition of this column vector will be a row vector 1, 0, 5. This is not 105. These are just 3 isolated elements, 1, 0, 5, right? Well, and what is it good for? Very, very important property of the transpose is the following. Imagine a matrix and a vector. We multiply the matrix with a column vector, and this is the vector. And if we compute the scalar product with another vector y, we can ask the question, can we move the matrix on the other side of the dot? And should we change the matrix or is it the same? So we can ask the question, what should be the matrix B such that the scalar product of x alone with by is the same? Well, and you may guess the answer is B should be A transpose. This is easy to see. The vector AX has the ith component equal to sum of A, I, J, X, J. And let's start with a square matrix. Let's start with the n by n matrix. So all the matrices will be n by n, and all the vectors will have n components. So x and y will be two vectors from Rn. In this case, J runs from 1 to n. And then the scalar product on the left-hand side is the ith component of the first vector times the ith component of the second vector. and I runs from 1 to n. And here, by has the jth component equal to bji yi. And here, I runs from 1 to n. You may ask, why do we denote the running index I and the resulting index j, and here vice versa? The name of the running index is completely unimportant. But this will be nice to compare the left-hand side and right-hand side. And on the right, we have the scalar product. So this is sum of products of j's component of x times j's component of by, j running from 1 to n. And then we use this relation for ax, and on the left we have sum over I, sum over j, and here we have the product a sub ij times xj times yi. And on the right, we have again the double sum. J runs from y to n, I runs from 1 to n, and then we have x sub j times bji y sub I. Well, and you see, well, we can change the order of summation because addition of real numbers is commutative. And if you compare what is on the left and what is on the right, we see that aij must be bji. That means A transpose is B. But this is a very dangerous moment. One might very easily make a big error, a big mistake. Oh, this is correct, but the reasoning is not yet good. From equation of sum, it does not follow the equation of the terms. Let me show you one funny case. A plus B is equal to 2 plus 5. Well, A must be 2, B must be 5. Really? No. What if you take A is 1 and B is 6? The sum is again 7. So you see, comparing sums is not enough to conclude that the individual terms on the left must be equal to corresponding terms on the right. Simply speaking, we cannot cancel the sums, and we cannot read just AXY is BXY, and from this AIJ must be BJI. No. This shows that this is a very bad approach. But in this case, it is true, because we want this to be equal Not just for some special vector x and special vector y. We want this to be true for all x and all y. So we want this to be true for all x and y from Rn. And now it is okay. Because if it is true for all x and for all y, we can consider the vector x to be 1, 0, 0, 0, and so on. And we can consider the vector y to be 1 and all the zeros as the remaining components. Then we can forget the sums because j must be 1, otherwise we have 0 term. And I must be 1 as well. So for these two vectors, we see that A11 must be B11. And then we can shift this 1 to a different position. But 1 will be just in one place, and all the other components, all the other numbers will be 0. So if we shift this to some special position, say alpha, then when summing over j, you can forget almost all the j's, just leave the term when j is alpha. And similarly, if we shift this y to a position beta, then I must be beta, otherwise we add 0. So A alpha beta must be B beta alpha. You see? So only when we consider the condition that this should be true for all vectors x and y from Rn, then using this choice and this choice, then actually picks up just one term here and one term here, and then this is 1, and then A is B with these indices. In a slightly more general case, when the matrix is not n by n, but rather if A is, say, m by n, then if the matrix A has m rows and n columns, then the vector x must have n components, and the result will have m components. And if the result has m components, then also y must have m components. And when x has n components, so it is from Rn, and this must be also from Rn. In this case, we have a different scalar product on each side. This is a scalar product of two vectors, each having m components, and this is a different dot. This is a different operation, scalar product of two vectors with n components. But everything works perfectly as well. Just we must be a little more careful with the dimensions. So AXI is this sum when j runs from 0 to n. So let me write it in yellow. And Y has m components, so this goes up to m. And then here I runs from 1 to m, and here j runs from 1 to n. This remains. And then here on the left, I is the index of y, which runs up to m, and this goes up to n. And on the right, again, j runs from 1 to n, so this remains, and I goes from 1 to n. And once again, if this should be true for all vectors x and all vectors y, this times we should rewrite this condition to all x from Rn and for all vectors y from Rm. And we come to the same conclusion that A sub ij must be B sub ji. That means A transpose is B. But this time, we not just move the terms in the matrix, we also rearrange the matrix in the form, if the matrix was very wide, then the transpose will be very tall, and vice versa. This property allows us to define transpose even of a linear operator in an infinite dimensional space. But this is not our problem for today. And similarly, as we can multiply two matrices, we can multiply a matrix with a vector. We can also multiply two vectors, namely we can build a scalar product. Sometimes we don't care about row or column vectors, but if we do, then the scalar product of two row vectors, the scalar product of two vectors can be considered as the matrix multiplication of row vector times column vector. So if X is a row vector, then the scalar product could be written X transpose X. And to distinguish row and column vector, it is important to do when we consider the product of a matrix and a vector. Because, say, if we have a matrix 2 by 2, then we can multiply with a row vector on the right, or we can multiply, with a column vector on the right, or by a row vector on the left. An example, a matrix 2, 3, 4, 5 times vector with components x, y will be 2x plus 3y, and the second component will be 4x plus 5y. If you write the vector on the right, and if you write it as a row vector, then this operation is not defined. Because when we want to build the scalar product of one row times one column, they don't match. Two elements, one element, not defined. But we can multiply a matrix by a row vector when we write the row vector on the left. xy times the matrix 2, 3, 4, 5. And the result will be 2x plus 4y and 3x plus 5y. So if the vector is on the left, it must be in a row form, and the result is again a row vector. But usually we write it in a way that the vector is on the right, and then it must be a column vector, and the resulting is again a column vector. Well, and perhaps if we consider if we consider these two results, you see they differ. 2x, 3y, 2x, 4y. Different result. And it doesn't help to consider the transpose to transform this row vector into a column. But if you change these two numbers, 3 and 4, then it will match. So if you want ax to be equal to x times some matrix, then we must take the transpose. And then the result will be again, if this will be a column vector, this will be a row vector. So if we transpose a row vector, we get a column vector. So, well, and if we transpose a transpose, we get the original matrix. So if we transpose what is on the, if we transpose both sides, we get XA transpose. And this is true not just for one vector, but for more vectors building a matrix. So if we have two matrices, say A, B, and we want to transpose this, then the result is B, this must be transpose. B transpose A transpose. Now A and B are two independent vectors in matrices. This is no more true. So for any two matrices for which the multiplication is defined, the transpose or the product is the product in the reverse order of transpose matrices to A and B. So that was for transposition of a matrix.